Okay, so we are back. So there are as you know, we have in the last class we looked at NFA, DFA, and all those things, right? And we looked at regular expressions, regular languages, certain properties. Now I will be so out of these four machines. Now I'm going to talk about push-down automata. I think I briefly started about push-down automata. So I'm going to give you one or two examples about push-down automata, then formal definition. Okay, and then roughly we say that how do you define language of push-down automata, right? We can describe that. Linear bounded automata normally I skip in the first introduction, and then we are going to look at Turing machine. So I think today we are going to look at Turing machine as well as some variations of Turing machines, because those are very useful for certain applications. And why we do this, as I mentioned earlier, in both DFA or NFA, there are languages which cannot be accepted by DFA or NFA. That means there are languages which are not regular, such as AN, BN, right? This language. So if you have this kind of language, AN, BN, so we cannot construct DFA or NFA because we require either infinite states, right, or some sort of memory track, right? So some sort of memory is required if you want to accept this. So that's the reason it cannot be accepted by finite state, but we can do it by push-down automata. And you know the idea is I will define what is push-down automata. As you know that it's finite automata plus a stacked memory where I can pop. I think I can pop or push something inside, right? So basically, the key idea is that I will keep on uh, pushing A on the stack n number of times, and then I will actually pop B same number of times. So basically, there will be some matching argument somewhere, right? You keep on doing this, and then you finish the input string, right? In that way, we will design the push-down automata to accept the language A and B, and that is the key idea. Okay. But then again, I would like to just mention that even there are languages which cannot be accepted by push-down automata. For example, if I just increase one more stuff here, so this can be done by PDA, not by finite automata. But if I take a language AN, BN, CN, so this cannot be done by PDA. Even PDA cannot accept it because we have only single stack, right? So if we add another stack, then we can do that. So a push-down automata with two stack, you can actually accept AN, BN, and CN also. But essentially, that in that case, the push-down automata is equivalent to Turing machine. Okay, so I'm not going to show you that connection, but at least you should know this fact. Okay, a push-down automata with two stack memory is equivalent to Turing machine. Okay, so what is Turing machine? Because you don't know, so I cannot talk about anything unless I explain those things, right? So this is the key idea. So there are languages which cannot be accepted by finite automata. So this is not a regular language, right? And in fact, the proof involves pumping lemma. Okay, so I'm not sure if somebody who is very much enthusiastic, they might be reading. Others may be busy in competitive programming, so that's okay. So, okay, so basically that is the key difference. Okay, so let me start with push-down automata. Again, thanks to Professor Bush, right? All the slides I'm using. So there is a key difference. This stack memory, finite automata plus stack memory. So there is an initial stack symbol, stack head, okay, or bottom special symbols appear at time 0. Normally, a typical transition is like this: you are in state Q1 after reading input on the tape A. what you do, you pop, so you do something to the stack memory. And what that something is, you pop B, okay, and push C on the stack. And then change the state to Q2. This is a typical scenario in a push down automata. Okay, typical configuration of the machine. You receive a input and you do some arrangements on the stack. Okay, so very basic arrangement is that you just pop one symbol and push something else, right, in this configuration. If this is lambda, you don't pop anything, right? Just push a symbol. C you can push on the top, right, and change the state. This is a very basic configuration. So here these are I think these are the examples which we have done last time. So A, B, C means what? Read A, pop B. You can see that pop is there on the. So you need to pop B. So B is there at the top of the stack. So essentially what you are doing, replace B with C, right? That's what you are doing here, right? And what does this means? You are just pushing C, nothing else, right? What about this? Just pop B and doing nothing. What about this? No change, no pop, no push pop business, right? No pop push business basically. First you do pop. Sometime I am confused which one is first, push or pop. Okay, so here pop is first and push is second. Fine. So normally we study non-deterministic push down automata here. So non-deterministic, you know, like for one input they have two choices, right? So here, for example, after receiving input A, I can go in this direction and also I can go in this direction. Everything works in the same way as NFA. Okay, there are parallel computations, so on and so forth, right? So this is something very important. And also there are lambda transitions. Okay, these are there, just state change. Remember, these are kind of delay in NFA. Similarly here also, this is a delay. You're just changing the state. So basically not reading the tape. So now let us see this beautiful example, A and B N. How do we accept this A and B N? I already told you the key idea. So you just read first A and what you do. So basically, in fact, you see, this is the start. This is the lambda transition anyway. So you are reading A, first A is hit. So what you are doing? Push A on the stack. And this you keep on doing unless you are receiving A as many number of times, right? Just fill the whole stack with number of A's, whatever that N is, right? No matter 4, 5, 6, 10, right? Then what happens? Once you hit first B, right? Start. What is this? Pop A. So every time you basically hit, basically, right? You do the same thing. First, next B, pop A. Next B, pop A. So now B, if you know B is also same number of times as A. So you're just matching. Right. Once the whole thing is finished, you just accept it. So let's see the whole idea. So basic idea, push A's on the stack, match the B's on input with A's on the stack. When once match found, you finally go to the accepting state, right? This is the key idea. So let us take a couple of examples with some strings so that it is really crystal clear to you what is happening here. So A, B, B, B. So obviously this should be accepted, right? We can see that first you go to the state Q1, then you read first A, and you push A. Next A, push A. Next A, push A. First B you read, first match is found, right? You pop that A. Next, another A. Next, another A. Once you hit $, you go to the accept. Right? So this is a really key, simple idea. So a string is accepted if there is a computation such that all the input is consumed and the last state is an accepting state. One important thing to worry about, what happens to the stack content? We do not worry. So basically, we do not care about the stack content at the end of the accepting computation. There could be some leftover, I don't care. Okay, in this example it was not, but in general, we do not worry about the stack content, okay, while doing the computation. Another example, I guess, yeah, so this is, what about AAB? Now you can clearly see that this will be rejected, right? Because the number of A's and number of B's are not same. So you read A, what you need to do? Push or pop? Push. Push A, push A. First B you hit, pop A, and then input is consumed. You're not in the accepting state, so you reject. Okay. Another example, VVR. So here actually we are sort of guessing the middle of this string. So it's like V and the reverse of V, right? All those strings made of A and B. So as usual, I leave it as a tea time problem for you. On your mobile, you can run. Of course, everything is here, right? I gave you one example, you can just work out. Push V on the stack, guess middle of the input, match with VR on the input stack, and match found, then you are done. So I leave it as an exercise. I am skipping this. So easy, right? Now we can define what is known as, so I gave you the basic idea. Now we can talk about the strings. So earlier in the stack, I was popping one symbol and pushing one symbol. Now we can pop whole string and push whole string. So that can be extended. So here the strings are W1 and W2. If we are in a state Q1, okay, after reading A on the tape, you pop the string W1 from the stack. So basically a whole bunch of symbols you are taking out of the stack and then pushing another string W, right? And then change the state to Q2. This is the basic when you operate on the strings. Another important thing is like these things are going on, and suppose you take a picture of the whole computation. You will arrive at some instantaneous description of the whole thing, right? So actually, that is called known as ID. I'll show you what is the meaning of ID. Anyway, so here it is an example. Pop EB and replace it with CDF, right? Push string, right? And you can do it with equivalent transitions. As you remember, always whenever you're handling the strings, we can decompose into symbol input symbols, right? So whole thing can be decomposed into bunch of smaller transitions. Okay, so now we go to the next. Yes, now formalities for the PDA, push down automata. So states, how do we define? So this string business, I can write, we are in a state Q1, delta function, input is A, your what is it, W1? Pop W1 and push W2, change state to Q2, right? This is what it is, right? And since it is non-deterministic, actually you can have more members on the right side, right? So in this case, for example, it is Q2 W2 and Q3 W3, right? Because of the non-deterministic, right, choice. So now formally definition. Now I think this is 7 tuple if I am correct, right? 1, 2, 3, 4, 5, 6, yeah. Q is the set of states, input alphabet, stack alphabet is also required. Then delta transition function, initial state, stack start symbol, and accepting states, right? F. 7 tuple we can describe. So now one thing is left in the PDA, which is how do we define strings? How do you define the language of the PDA? Anyway, so as I mentioned, this is ID, instantaneous description of the whole machine. At any point of time, we are in some state Q. There is some remaining input on the input tape and some stack content, right? Current stack content, right? So these are the three variables essentially which you should look for every time you are doing the computation, right? QUS. And now this will keep on changing. So one ID, another time interval, another ID, another time interval, another ID. So actually, computation start from the start state Q0 with one ID and keep on moving until you get the QF, the final thing, right? State. So here is an example. So for example, this machine here, We are in state Q1, right? So state Q1, comma, what is B? So basically you are going to read this B on the tape, right? That is left. And then A dollar is the stack content. So this is the one of the ID. The whole machine can be described in these three things, right? Okay. Similarly, now ID change. So Q2, you see, the state changes to Q2, BB, and AA dollar, right? So essentially, we can write from this ID, we move to this ID. This means, how do you pronounce it? Anyone in the class? ये तो हाई स्कूल में है ना? Okay, very good. So I leave it as an exercise. Just find out what you call. How do you pronounce it? I can tell you right away, but I think you should. So if you are poor in English, you can assume that this symbol represents move from here to here, right? This is kind of move, okay? But you need to tell me what is this symbol. Okay, so basically the whole computation can be described starting from that ID, initial ID 1, you move to another one, move to another one, and so on with the final one. Whole computation can be described in these IDs, starting from the start state and moving to the final state, right? Okay. So this motivates us to define the language of the push-down automata. Mathematically, how do we describe? We can describe in terms of these IDs. Okay. So the whole thing can be written as starting from this ID, in 0 or more move, I arrive at this. 0 or more move means this star. What is the symbol that you will find out? Okay, so the language of the push-down automata is all those strings such that starting from the initial state, and that is the ID. In 0 or more move, we go to the accepting state configuration, right? That is the language of the push-down automata. So again, one thing you need to find out, given a language, find the push-down automata. You should have that practice. I think assignment number 1 has that examples. Given a push-down automata, find the language. These two things you should learn. Yes. No, 0 or more move. All the things are there. Yeah, that will come, right? I'm saying that from the starting state, all those strings W, such that from the initial ID, you go to the final ID. And of course, from initial ID to final ID, there will be a bunch of moves in between. Okay? 0 or more moves. Okay, so I think you see, for example, this B belongs to this language because from the initial configuration, you can go to the final configuration, right? In bunch of moves. That number of moves might be different every time, depending on which string you are looking at. So A and Bn belongs to this. So language is this. Done. So push down automata is done. These slides are beautiful, right? So now you see. So now we come to the next machine. I'm going to talk about Turing machine. Turing machine is a beautiful concept, as I mentioned, discovered by Alan Turing in 1936 because he misunderstood the question that was asked by David Hilbert. It's all accidental discovery of computer science, you see. What would you have done if there is no computer science? What happened to your jobs? right? So sometimes, this misunderstanding is very useful. So the language, I mean, the question that he asked, whether there is a, as I mentioned, the David Hilbert asked this question, whether there is a mechanical procedure through which we can decide, whether some statement, or how do you prove something, in a logical way. Is there a mechanical way? So mechanical means Alan Turing thought that he's asking for a machine, and then he started building this machine. Okay, and that was the fundamental thing in computer science, right? It turns out to be very fundamental thing. So whenever we are discovering computation, so I think, for example, you should know that you can do computation. Somebody has shown that billiard board games, right? You have seen billiard ball games, right? You just push the balls. You can do computation through that also. So Turing machine thing can be done from there. You can also do computations. Have you, by the way, there is another very interesting thing. How many of you know about Minesweeper game? So some of you might be initial Windows. They might. I hate Windows, but by the way, you might be. You might have seen that Minesweeper game, right? Minesweeper game can help you in winning $1 million just playing by the game. So bunch of logic circuit you can build out of Minesweeper game. So if you search on Google, you will find interesting things. Okay. Minesweeper game and P versus NP problem, which I mentioned in some time back, it has a very good connections. Okay. So Minesweeper game, just play that and earn $1 million. Anyway, so whenever we are discovering any computational process, it is easy for us. We want to know, for example, okay, you are making in the social media, right? In your Facebook, you are making a new friend, right? Can you predict who will be the new friend in the whole network? So you can do those kind of things because it's a computational process. Now, when I say computational process, you want to match it with which kind of machine? Because there are only 4 kind of machines. It will match to either this, that, or this, right? So you want to understand the computational power of that computational process, which one is acting there. So once you do these kind of analysis, right, you can actually predict who is going to be the next friend in your network and so on and so forth, right? So, it's a very beautiful application, powerful, beautiful mathematics, right, sitting everywhere. So, if you know that this whole thing is Turing is equivalent to Turing machine, so basically, you can actually know that what can be done and what cannot be done with this computational process, right? What are the possibilities? That's why it's very, very useful. But normally Turing machine has infinite tape and some alphabet, right? So with minimum number of alphabet, what kind of computations can be done? So there is a lot of examples by Wolfram. You know about Wolfram, Mathematica person, right? So he has done, interesting, actually, in fact, he announced uh, a competition also for certain things. You want to minimize the basically optimal Turing machine for doing certain computations. Minimum number of alphabets should be used for doing certain computations. Those kind of competitions were there, and I think some students won that competition some time back. It's really a beautiful thing, by the way. How many of you are using this generative AI? All of you for doing homeworks? No, I think half of the DA is using that, right? Chat GPT? No. Anyway, so again, thanks to Professor Bush for these. Uh, so we have regular languages which can be accepted by DFA or NFA. We have context-free language. I'm going to talk about what is context-free. So basically, the languages which are accepted by push-down automata are called as context-free language. Okay, and then there are languages like AN, BN, CN which cannot be accepted by push-down automata with single stack. It can be accepted by push-down automata with 2-stack memory. Okay, so this is the language hierarchy. I'm going to talk about more of these things in next class. So Turing machine accepts AN, BN, CN as well. So what is this beautiful concept? There is an infinite tape. Okay, So it's a thought computer actually. You see, it's you know how Turing has thought about it. It's a it's basically a tape. We can assume that in infinite tape on both sides, and in somewhere you can read write head, which can write something or erase something like that here on the tape. And there is a control unit. This is same your finite automata business. So with the finite automata, you also having a tape. Okay, that is the key thing here. Now, so there are no boundaries in finite length. And head can move left or right. I'm going to give you a very basic Turing machine. There are many variations which we'll talk about it later on. The head can move left or right. So the head of each, the head at each transition, reads a symbol from the tape, writes a symbol, and move either left or right. Every transition, it does three things. Number one, read a symbol on the tape. So maybe then replace it with some other symbol or write something, or move left or right. These are the three operations that it does. So for example, here, tape situation is, so tape content is ABAC at time 0. At time 1, you can clearly see that arrow is pointing towards A. So arrow is reading A, reads A. Then writes K. In place of A, you write K and move towards left. Now you are reading B. Okay? Head is pointed through this arrow, what it is doing, right? So this is the whole scenario. Similarly, another example, ABKC, AFKC. So reads B, writes F, and move towards right. You can clearly see that, right? So normally, to distinguish between the input and the other content of the tape, so input is, for example, A, B, A, C here, and these blank symbols we use. Make sure that between blank symbols, we have the content that we want to do the computation with, right? That is the content. Okay. So head starts at the leftmost position of the input string. So this is a typical assumption. You start the computation by reading the leftmost symbol on the tape. All right. After the blank symbol, whatever is the first thing, you read there from there, right? So what are the states and transitions? So here are the typical configurations. This means you are in a state Q1, read A, write B, and move left, and the state change to Q2. So read A on the input, write B on the tape, and move towards left, and state changes from Q1 to Q2, right? And then here you are in a state Q1, read A, write B, and move towards right. So L means left, R means right movement. Okay, this is the typical scenario, states and transitions. Now look at this. Current state is Q1, you are reading A. So A replaced with B and move towards right, and the state changes to Q2. So how it looks like this. See? A is replaced with B and then move towards right. Now you're reading C and the state changes from Q1 to Q2. Okay? Very simple. Read A, replaces with B and move towards left. That's what you have done here, right? Read blank symbol, replace it with G and move towards right. You can clearly see that, right? Now, Turing machines, we normally study deterministic, and as I mentioned, there are non-deterministic Turing machine as well, but I'm not going to discuss any of those things. So for a different input, we can move different directions. That is okay, but for the same input, we cannot move to different directions, right? That is a key thing, right? So in these ones, I'm going to show you deterministic Turing machine. Okay, and there are no lambda transitions allowed. Okay, we are talking about deterministic Turing machine. And partial transition functions. Sometime it may happen for some input symbol, there is no transition that is allowed. Okay, partial transition function. Now I think we are ready. How do we halt a machine? Machine halts in a state if there is no transition to follow. Then machine halts. Okay. With this preparation, now look at certain examples. Here, no transition from Q1, so we don't know what to do. Machine halt. Reading C1 and that's all. Another example. We are in state Q1, we are reading C. So in the machine, we don't know what to do when you are in state Q1 and symbol is C, right? So no possible transition, so you halt, right? Now, another assumptions like this kind of things are allowed, right? Accepting states have no outgoing transitions, okay? So this kind of things are not allowed. Accepting states, here I am showing you a outgoing transition. This is not allowed. Okay. So that is allowed, okay, at the top. So how do we accept? We accept the input string if machine halts in accepting state. We reject the input string. There are two cases. If machine halts in a non-accepting state, sometime it enters into infinite loop also. I will show you an example how a machine can enter into infinite loop. Now you can think that when you're writing programs, sometimes it happens that it goes into infinite loop, right? Because it is all equivalent to Turing machine, right? So it's a beautiful thing you can observe here. So in order to accept the input string, it is not necessary to scan all the symbols in the string. This is very, very important. That's why for certain symbols, we don't know what to do, right? Now take an example. Now I'll do a bunch of examples and then formal definition of Turing machine. And then after that, we'll talk about variations of the Turing machine. So input alphabet is sigma is equal to A comma B. A star means all possible strings of A, right? So now here is the Turing machine. What it does, start state, you are in a Q0 state, you start a state, read A, move right, read A, move right. No matter how many A's are there, until you hit first blank symbol on the tape. Suppose tape has 5 A's. So till 5 A's, you will keep on reading until you hit the sixth one, which is not A but a blank symbol. And then you move towards left and stop. Okay. So here is a working example. So we have A, read A, move right, read A, move right, read A, move right. You hit blank symbol. Once you hit blank symbol, what you do? We are just saying that, so this diamond going to diamond L means what? You just move towards left. Halt and accept. Got it? So really these are the very easy things, right? Rejection example, ABA. You read A, move right. Now you don't know what to do after reading B. No possible transition, so halt. And now you are not in the accepting state, so reject. Okay. Here is a simple machine. This accepts the language A star. Okay. We halt and accept. No necessary to scan the input. Not necessary to scan the input. That is also a possibility. I think you require a tea break or something, right? Because some of you are tired. Anyway, so we can give 1 minute break. You can take yoga. I mean, you can do yoga and then you can start. So now I'm going to give you infinite loop thing. So you can see that the machine enters into infinite loop. This is a very beautiful thing, right? So this machine is here. When you read A, move right. You read B, move left. I mean, you can clearly see that this will get a problem. If the string has, keep on doing this kind of problem, right? So it will just keep on in the infinite loop, right? So let us see the example. ABA. You read A, move right. You read B, move left. Right? You can read A, move right, and keep on doing the infinite loop business, right? This is a possibility. Okay, so Turing machine can enter into the infinite loop. This is a possibility, right? What? क्या? But delta transitions नहीं. Sorry, lambda times नहीं, lambda times delay कर सकते हैं. Okay, so I think because of the infinite loop, the accepting state cannot be reached. The machine never halts. The input string is rejected. Now, this example. So I'm going to give 2-3 minutes about this example. This is the basic understanding, and we will use a similar trick for adding two numbers. If I want to add two numbers using Turing machine, what you should do? Or you multiply two numbers, or subtract two numbers, or do any arithmetic with the Turing machine. How should we do that? Okay, so the idea is similar. I can again explain to you what we are. So when we want to accept language A and Bn, so remember in the push-down automata, what we used to do for A and Bn, you keep a track, right? You push, pop, same number of times, right? So there is some sort of memory which you are keeping a track. Here, what I do, I read A, replace it with X, read B, replace it with Y. And this is how we are keeping track of the memory, right? How many times you replaced. Okay. And finally, when it is matching, we accept. Okay. This is the whole idea. All calculation is doing this simple idea. Okay. Read A, replace it with X, read B, replace it with Y. You see, basic idea, you have to match number of A's and number of B's. So what you do, repeat this all the time, replace leftmost A with X, leftmost A with X, find leftmost B and replace it with Y. So basically, on the string, you read first A, replace it with X, go to read first B. There may be in between many A's, you skip them. Go to the first B and replace it with Y. Then again come back and read the next A, replace it with X, go and again go to the next B and replace it with Y. And this is how you continue. Until there are no more A's and B's. If there is a remaining A or B, reject, otherwise you accept. So here is a trick. So look at this A, B, B. So this machine, starting from the start state, read A, what I need to do, replace it with X. Now I am not replacing the next A with X. Now I should keep a track. So I go and read first B. That's why there is a movement, right? Go to the next one. Then replace this B with Y. Then you come back and read the next A, replace it with X. So sorry, you are again coming back the beginning. Then replace it with A with X. Keep on going, replace V with Y. And then finally you accept. Again, I should mention that the answer of some of you could be different while designing the Turing machine, depending upon how many states you're using and what kind of scenario you are doing, right? So answer may be different from this guy or that guy, right? That is a possibility. So finally halt and accept. So remember, again, this is a convention that we stop towards the last input of the symbol, and there you put the string in whatever state, that is your final accepting state. So again, a T-time problem, the same Turing machine, you need to modify to accept this language A and B and C N. This time, I can give you the idea. Read A, replace it with X. Read B, replace it with Y. Read C, replace it with Z. And whole business you can continue. Rest of things can be easy when you have a cup of tea, right? Just drawing the things. Okay? I hope you can do that. Not very difficult, just some extension to that machine. So formally, I think variations we will do tomorrow. Okay. I'm going to do at least this much. So transition function, how do we describe? Transition function. So, read A, replace it with B, move right, right? This can be written like delta of Q1A is equal to Q2BR. Right? You are in state Q1, reading A, state change to Q2, replace A with B and move towards right. This is the transition function. How do you describe? This is another transition function, right? For the other above operation. So formally, Turing machine is also a 7-tuple. Q, set of states, sigma input alphabet, gamma tape alphabet, delta transition function, Q naught initial state, blank symbol or diamond symbol, right? Accepting states. Now, one question that I'm going to ask you, you may use ChatGPT many times, right? So whether a Turing machine can have multiple accepting states or not. Okay, so use ChatGPT or think about it. So configuration. So here, just like in push-down automata, we have instantaneous description ID. Here we have a configuration of the machine. So ID is here. See, the machine is reading symbol B. You are in a state Q1, and the tape content is CABA. So CA, you insert Q1 in between and BA. So Q1, we are in a state Q1 and reading B. That can be described like this ID, right? Shorthand for the one description. Similarly, another configuration. So you move from one configuration to another configuration, right? So that means we can start with the start state and bunch of 0 or more moves. We can arrive at the final ID. Here is this finally. So we have starting from here in 0 or more moves. 0 or more moves, I arrive at this. This is the final, from there to there. This is how you describe whole step of the computation. So initial configuration Q0, the whole string is W. Fine. Input string. So language of the Turing machine is all those strings W such that from the initial configuration in 0 or more moves, you arrive at the final configuration. Right? Everything is very intuitive, obvious definitions. So if a language is accepted by a Turing machine, then we say that L is Turing recognizable. Other names are Turing acceptable, or another very common name is recursively enumerable languages. Okay. And there is a reason why we call them, but I think that's okay if you don't know about it. You want to take 1 or 2 minute break, then I can show you how to compute using Turing machines. So you understood basic idea about Turing machine, how to accept certain languages, right? So one example, if you do A and B and C and you will understand the whole business, right? And then how do we compute? Now if I have to add two numbers. So here we use unary alphabet. What does that mean? So if I want to add 5 and 3, so 5 and 3 is 8. So what I do, those 5, I will encode it as a 1, 1, 1, 1, 1. So 5 ones. Put it on the tape. Then insert a middle symbol just to differentiate this input. And the second input you can put on the tape as 3 ones, 1, 1, 1. Okay. And then blank symbols all together. Now you do some computations such that this middle symbol is, you can take it out and all the content is together. 5 ones plus 3 ones. So total 8 ones are there, right? You can see how many ones are there. So that is how you do the sum. Now how do you do this? You read first one, replace it with X. Use second one, replace it with Y. Those kind of things you need to do. So I am going to show you in details. So a function is, is a rule which associates to every member in domain, giving unique image in this from your calculus class, right? So addition function, it has two parameters, X, Y. So we are looking at unary domain in the Turing machine. It is easy to do the business. We prefer unary representation. So we say that a function is computable if there is a Turing machine M such that with initial configuration like this, Q0W, we have the final configuration F of W on the tape for all W in D. If you can do this, we say that the function can be computed by the Turing machine. Or in other words, a function is computable if there is a Turing machine M such that from the initial configuration Q0W, in 0 or more move, we arrive at the final configuration for all W in the domain. So if I want to show that the function X plus Y is computable, X and Y are integers, Turing machine X, I put 0, Y, input tape, output string should be XY 0, XY together. So means total number of sum is obtained, right? I'm assuming everything is integers for easy, you know. When you want to add integers, then. So by the way, you know that you can also do arithmetic with DNA. So one of my student created DNA calci. So you can do bunch of DNA strings can do these kind of arithmetics for you. Again, it uses some idea of Turing machine, which you can look at it later on. Anyway, so here is the x number of ones, y number of ones, and delimiter 0 to distinguish the two numbers, right? And final state is x plus y. So question is, how do we? What is 0? No, x is how many ones are there basically? Oh, you are saying no, here we are assuming positive numbers. I'm showing you. I mean, you can always do modifications when that happens, what to do. Okay. I'm assuming even x and y are only integers. You see, you can even go for the higher thing. The only thing is the machine will be more complicated, right? And you will enjoy the beauty, right? So, yeah.
We can change the 0 to 1 and then move to right.
Yes. Right. Okay, so some people are getting the idea how do we do this computation. So let me show you. So final is this, right? X plus y. Here is a machine for adding. For adding x plus y. So you see, you read 1, move right. How many ones are there? First 0 is there, which is delimiter. Then what you do? Let us look at this example. This is a Turing machine. Example is 1 1. X is 1 1. Y is 1 1. Right. So then. So I know it may be too much for you, but anyway, it's okay. X is, you read 1, move right, read 1, move right, read first 0, replace it with 1, keep on going until you hit the blank symbol. Once blank symbol means input is consumed, come back, replace last one with 0. Right? The idea is very simple, right? And then you keep on, I mean, this is what you need to do sort of, to make sure that you arrive at. So here they are stopping at here. Okay, that's also something you can do. Yeah, this way or that way. They stop you can do here and there, whatever, depending upon the convention. Anyway, so this is how you add two numbers. Okay, so if I want to add 2x, if x is you want to double the number, again use the same thing. This time y is equal to x, right? So you can do that. So sometime, depending upon what you are doing, things can be simplified, or depending on if you're doing more complicated computation with the Turing machine, it will be a bit complicated machine, right? So that's why we need some sort of variation on the Turing machine, which we are going to talk about tomorrow, how we can do the variation on the Turing machines. So I think in the exam, I asked you the sample paper, take the string and reverse it. You have to design the Turing machine for that, right? तो ये सब तो प्रैक्टिस से ही आता है बेसिकली. चैट जीपीटी तो मदद करेगा नहीं, right? So I think you need to do some practice. Now if you have function like this, fxy is equal to 1 if x is greater than y, 0 if x is less than or equal to y. So input is x, 0, y, output is either 1 or 0. Okay, this kind of thing can be done. This is the pseudo code. So essentially now this is the pseudo code for Turing machine. You know what you do. Match 1 from x or 1 from y until all x, y is matched. If a 1 from x is not matched, erase tab, write 1, else erase tab and write 0. So there is a very nice idea about combining Turing machines. This is a block diagram, one Turing machine, input, output. So we can have one Turing machine for comparing, another one for adding, another one for eraser, and so whole thing we can compute the whole business, right? This is the whole idea, but actually Turing machine, the deterministic Turing machine, the model which I discussed, becomes more complicated for complicated problems, right? So then there are variations of the Turing machines which are very, very important. And normally people use that variation to show that something is equivalent to Turing machine in terms of the computing power. Done. So I think that's all for Turing machine. Now, next class, I'm going to talk about variations of the Turing machine. Then I think one topic you might have come across in calculus. Have you done countable, uncountable business? So I have to cover that also. So basically, I'll tell you the idea. The idea is, I will I will show you that there are countable Turing machines. Okay, collection of all Turing machine is countable, and there are more languages than the Turing machines. So that means there is a Turing barrier, and for that we use countable and uncountable of calculus. That idea. Okay, so that I will show you in the next class. Variation of the Turing machines and that there are more languages than the number of Turing machines. Okay, so that is the key idea. And after that, some little bit of grammar. So next class is the last class, right? So it will be done very easily, right? So I hope you are enjoying the course till now. Probably next class will be my last class because I am away for 1 month. So Professor Kundu will take care of rest of the stuff. Then I'll come back on the, I guess probably around, so I think after algorithms. So maybe on the recurrence relations we will talk about. I will come back again, right? But anyway, all the videos are available from the previous class also you can enjoy. And I'm available on WhatsApp 24/7, right?